Greetings, peeps. Our next topic is work, energy, and the conservation of energy. Hey, let's start with defining kinetic energy, the energy of motion in terms of its physical quantities. But first, whoa, dizzy. Oh, I hate it when that happens. But I wanted to be with you in some capacity. My avatar is back. He'll hang with you throughout to guide you through the various pieces of information which you will discover. Okay, kinetic energy is equal to 1/2 mv squared. M is mass in kilograms. V is velocity in meters per second. These are quantities which we're familiar with. We are familiar with mass. We're familiar with velocity. Together, when they're combined in this way, they give us kinetic energy. We'll see how we get that momentarily. Like the physical measurement of work, kinetic energy is measured in the unit of joules. It's a scalar quantity. What does that mean? Scalar quantities do not have direction, unlike their counterpart vectors. So with a vector, you can say, I have been traveling 5 meters per second east, but you can't say 50 joules east. That doesn't make any sense. Joules are just an amount. It's the amount of work performed on an object or the amount of energy possessed by an object. And there is no direction, which in some cases actually makes it easier to work with. Let's take a look at how work and kinetic energy are related. Believe it or not, they're related through the work-energy theorem. The net work done on an object equals its change in kinetic energy. So, how's that exactly? It is, getting a little mathy here, equation 1 and equation 2. Let's take a look at how these combine to give us kinetic energy. So from work, we start with work net equals F net times D. F net is the net force in the direction that is parallel to the displacement. Okay, so we got to realize that this is the parallel force, parallel to the motion of this object. And of course, F net, we realize from Newton's second law, is ma, mass times acceleration. So if I substitute that in, we get really mad. No, it's MAD. Mass times acceleration times displacement. Okay, equation number 2 should be familiar to you. We have VF squared equals V naught squared plus 2AD. This equation comes from your smileys. It's the one without time. It's the one on the bottom. And we're going to combine these together. Notice that both of these equations have a term with AD. So if I solve for AD from equation number 2 like this, I subtract V naught to the other side. To isolate the AD, divide by 2, which is the same thing as multiplying by 1/2. 1/2 VF squared minus V naught squared equals AD. And I take this AD, put it up here in the work net equation, equation number 1. And here's what we get. Work net equals 1/2 M parentheses VF squared minus V naught squared. And then if I distribute a little bit here, the parentheses, okay, 1/2 M. We got 1/2 M VF squared minus 1/2 M V naught squared. What this says here, remember kinetic energy was 1/2 mv squared, says that the net amount of work is equal to kinetic energy final minus kinetic energy original or not. And so this, anytime you've got the difference between two things, that's the same thing as saying the change in. So we have the change in kinetic energy. So if you perform work on something, you automatically change its kinetic energy, the amount of energy of motion that that object has. So you can think about it now. If you start off with no velocity, V naught is at rest, and then take it to somewhere else, you're giving it some kinetic energy. You're starting from 0 and you're going to some value over here. So it's the change in kinetic energy. All right. So that's the nice thing about work. You will change it in some kind of way, that kinetic energy. All right. Gravitational potential energy is a little bit different. Okay. We have a different type of energy here in that anytime there's a gravity field, so we have one on Earth, right? We're hanging out here on the surface. And you can look over here at A. We've got a 2-meter cliff here and a 200, it takes 200 joules to raise this to this height over here, because if we look over here, it's 100 newtons, okay? The weight is 100 newtons, and if I raise it 2 meters, I've moved it 2 meters upwards, and the amount of work performed would be 200 joules. If I were to take it up an incline, the distance is greater, the force is less that I need to apply here, which is the reason for the ramp. It's a little easier to push it up, but in the in the end, we do the same amount of work. The math actually works out, if you do the trig, that moving it 4 meters at this angle over here with a force that is less than 100 newtons would provide an energy, again, of 200 joules. As long as you raise it 2 meters, it doesn't matter how you get there, whether it's straight up the cliff, up a ramp, or up the stairs, you're still doing the same amount of work. So this is why when we do our stairs lab to determine the most powerful person in the class, we can use stairs and determine the amount of work performed on our own bodies. The amount of work that it takes to perform against gravity is going to be dependent on our weight and the height that we move upwards. Okay, so of course if these things were to fall, then we can consider gravity doing the work. So if this thing were to fall 2 meters, gravity would perform work in the opposite direction. So depending on the convention, it could be positive work or negative work, depending on which way you call positive or negative. All right, so let's check out a situation with gravitational potential energy by looking at the variables first. Gravitational potential energy is, well, force times distance, force net times the distance. The force net is the weight, mass times the acceleration of gravity, mg, and the h is the reference above wherever you start. So if you start on the ground, that's a nice reference. It doesn't have to be the ground, but it's a good one to choose. Then raising this will give that object gravitational potential energy. It has the potential to be converted into another type of energy. It has potential to move. And that's why we call it potential energy. So you'll see what I mean when we talk about the conservation of mechanical energy. So here we go. Conservation of mechanical energy says that the energy final is equal to the energy initial. So whatever we start with, whatever energy we start with, is the energy we end with within that system. If we look within the system, this is the case. There may be situations where energy leaves the system, but overall, if you take the system to be like much bigger, we always have conservation energy in some kind of way. It's one of the key fundamental properties of science and physics. So in terms of the two energies we've talked about, we've got kinetic energy and gravitational potential energy. So sum of the gravitational potential energy and kinetic energies in the sum of the final equals the sum of the gravitational potential energies and the kinetic energies original. Okay, pretty simple. Cool. So let's check this out. Got a situation here. Poor woman. Oh, I'm so sorry here. She's having a bad day, but at least she's still got her purse, and she's jumping out of a burning building. And so she starts off with some gravitational potential energy that happens to be 10,000 joules. So whatever the mass, her mass is, times gravity times the height would be 10,000 joules. And so she starts off with a v naught of 0. Okay, there's no initial velocity. She's at rest as she jumps out the window, vertically speaking here. So kinetic energy is 0. But a moment later, whoop, she's now transitioned some of her potential energy into kinetic energy. This is called a conversion. She's still got her purse. It's falling at the same rate. Notice. Yes, you did, right? Potential energy is now 7,500 joules. We've lost 2,500 joules as the height decreases, and we're gaining kinetic energy because she's gaining velocity. So there's this trade-off here. When we lose gravitational potential energy, it's converted into kinetic energy. At some point here, they're equal. Halfway down, because height is half, she'll have 5,000 joules of gravitational potential energy and now 5,000 joules of kinetic energy, and she continues to gain velocity as she moves down. Now she's looking kind of supine, so I think she's kind of given up. She's just like, all right, I don't know what's going to happen over here. This could be dreadful. I don't know. Well, all right. Now she's freaking out. She's screaming. Her hair is going up. Her purse is further away, but still at the same height. Okay, potential energy is now 2,500 joules. She has mostly kinetic energy over here. And I think, what's next? What's next, I think well, I think it's going to be 0 potential energy when she hits the ground, no height, and kinetic energy will be at 10,000 joules. And after impact, wait! Hey! There's these dudes down here. Wait a minute! I know this guy! He's the guy with the beard from Solapur, India. This is the baby catcher! Oh, right. Well, they have axes too, but you know what? These guys were trained in Solapur. They're going to catch her. Everything's fully safe. and lady in distress is going to be just fine. You know what? It's good these guys practice catching babies because they're going to save people's lives in the future. All right. Here's the big picture of the whole thing, the whole scene, if you want to check that out. So starting off with 10,000 joules of gravitational potential energy, ending with 10,000 joules of kinetic energy. The sum remains constant, always 10,000. So, more with conservation of mechanical energy. Let's take a look at it in more detail. So, we saw this before, that energy final equals energy initial. And sum of the kinetic energy final and gravitational potential energy final, blah, 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 blah. But here's the detail that I wanted to bring up. Anyway, the new stuff is now we can piece it out in terms of variables, motion variables, and also property of mass. 1/2 mv squared, that's the kinetic energy, plus mgh, so this is the final side, is equal to 1/2 mv naught squared plus mgh naught. So in this case, this equation may be very useful in making some predictions. Notice though, notice very curiously, that mass cancels in every one of them. We can cancel the mass, so mass really doesn't matter when it comes to the conservation of mechanical energy, which is pretty freakish, but that's because all objects fall at the same rate, where we're talking about the lady's mass or the purse or anything like that. So we could figure out things in terms of velocity, gravity, and actually kind of what we get pretty much out of this is what do you say, the fourth equation in the Smileys. So it comes from the conservation of mechanical energy, and so this will be pretty useful when we need to solve for certain variables in certain situations. We could think about a falling object, one moving down a ramp, in different terms that may be simpler to analyze. All right. Yes. All right. Here's an interesting situation. Skidding distances, stopping distances, and related to their velocities. This is in kilometers an hour. So from 30 kilometers an hour, it takes 10 meters to stop. If you double your velocity, it takes 40 meters. So it's because of this square relationship. So it's something called inverse square that we're going to study later. But this is a weird thing. And if you go double again, it would take another, let's see, quadrupling of distance over here. So if you were to quadruple this distance, the quadrupling squared is 16 times. So in other words, your stopping distance is proportional to the square of the velocity, which means that, well, you should go slow. Because if you go fast, it takes a lot longer to stop. If you go twice as fast, it takes 4 times longer to stop, which makes things kind of dangerous. So I know you guys are going for your licenses and whatnot, or some of you have them. Here's a nice lesson for you. The stopping distance, you need much, much more room due to physics to stop safely. So you need 4 times as much room going twice the speed. Hey, here's a pendulum. We're going to study pendulums later, but it also observes the energy transformation, conservation of energy. So we've got gravitational potential energy starting over here. We let go of the bob. This is somewhere in between. We've got some gravitational potential energy because it's still falling, and now some kinetic energy at the bottom. We got all kinetic energy, and whoop, back up to the top, all potential energy. This kind of reminds me of, well, your projects, in that you can store energy in a spring. Springs have the ability to store energy. So a lot of you guys are using bungee cords, or some type of rubber band, or some tension. This tension is a storage of energy of some sort, and so it's called elastic potential energy. So our projects, most of them for the tennis ball launchers, will utilize some kind of potential energy in the locked and loaded position. So you might have something like this. Again, a bungee cord, you may have springs, you may have some kind of device, a torsion, twisted rope. It's all energy, and some of that energy will actually go into the motion of, in this case, the car, or the motion of your lever arm to throw the ball, but some of that is wasted as heat. So heat is a thing that we'll talk about in terms of one of the potentials that take away from the system. So it means that the system's not 100% efficient. We will lose some energy to the environment in the form of noise, vibrations, and heat. Okay? But as a total, if you consider all that stuff, it's not fully lost if the system is external to the car, but the car, you know, we start off with 10 joules of potential energy here. We only have 8 going into the motion of the car. So we consider it a loss in terms of the car, but not an overall loss in terms of the system. So, Fiend, Morad, out.